Right now, as you're listening to this, microscopic particles of antimatter are raining down from space.
Yeah, it sounds completely absurd, doesn't it?
It really does. I mean, they are passing through the roof over your head, and they're actually annihilating inside your body right now.
Which is just a wild concept to wrap your head around.
Totally. Because the very word antimatter just feels like, I don't know, something that only exists to move a science fiction plot forward.
Right, exactly.
You picture glowing warp drives or, someone in a uniform shouting about a containment breach.
Yeah, it definitely carries that Hollywood sheen. We have totally been conditioned to think of it as just a fictional trope.
But it's not.
No, not at all. Antimatter is a 100% factual part of our universe. It is routinely created in laboratories. It's part of the natural decay of the world around us.
Right.
And honestly, its sheer existence is tied directly to the deepest mystery of why human beings, or any physical objects at all, even exist.
And that is exactly our mission for this deep dive today. We are taking all the sources and stripping away the science fiction tropes to look at the actual physics.
Because the reality is so much better.
It is. How it works, how we discovered it, and what it implies about the birth of the universe. It's infinitely stranger than anything a screenwriter could invent.
It really is. And to appreciate just how strange it is, we need to take a quick, unhurried look at the baseline first.
Okay, the baseline. So ordinary matter.
Right. The ordinary matter that makes up you, me, and the device you're playing this audio on. Most people are familiar with the basic model of an atom, right?
Yeah, you have a nucleus in the center.
Exactly. A nucleus in the center, and orbiting around that nucleus are electrons.
And the defining feature of those electrons, well, at least for our story today, is that they carry a negative electric charge.
Yes. They are negatively charged, and the protons in the nucleus are positively charged.
Right, they balance out.
Precisely. That balance of positive and negative is the absolute bedrock of chemistry, biology, essentially everything we can see and touch.
And for a long time, physicists just kind of thought that was the end of the story, right?
They did. But then, in the late 1920s, you have this British physicist named Paul Dirac, and he was sitting at a desk, not, running physical experiments in a lab, but doing highly complex mathematics.
Right, I read about this. He was trying to force a sort of mathematical marriage between two areas of physics that notoriously hated each other.
That is a great way to put it, yeah.
It was quantum theory, which governs the weird behavior of the supertiny, and Einstein's theory of relativity, which deals with things moving incredibly fast.
Right. Dirac wanted a single, elegant equation that could describe an electron moving at nearly the speed of light.
Which is no small task.
No. But he succeeded.
Yeah.
He wrote an equation that perfectly unified those concepts. But, and here's the catch, there was a bizarre mathematical artifact hidden inside his work.
Yeah, this part reminds me of basic algebra.
Oh, how so?
Well, if I ask you for the square root of 4, the obvious answer is 2, because 2 times 2 is 4.
Right, simple enough.
But negative 2 is also a technically correct answer, because a negative times a negative is a positive.
That is actually the perfect way to visualize what happened to Dirac. His energy equations basically had two valid solutions.
Okay.
One described the ordinary negative electron that everyone already knew about. But the math stubbornly insisted on a second solution, a sort of mirror image particle.
A mirror image?
Yeah. It had the exact same mass, the exact same properties, but an opposite positive charge.
A positive electron, which at the time must have sounded insane. I mean, it was considered physically impossible.
Completely unheard of. Many physicists actually told Dirac to just ignore the second solution.
Just pretend it's not there.
Exactly. They assumed it was just a quirk of the math, a leftover artifact that had no bearing on reality whatsoever. But Dirac, he trusted his equations.
He stuck to his guns.
He did. He argued that if the math required this mirror image particle to exist, then nature must actually contain it somewhere.
It is like, balancing your monthly budget at the kitchen table, and your spreadsheet's perfectly balanced, but only if you acknowledge a secret parallel bank account you have never once seen.
Yes. Yeah.
You would assume you just carried a 1 somewhere and messed up the math. But just a few years later, Dirac was proven completely right.
He was. In 1932, experimenters were studying cosmic rays. Those are high-energy particles crashing into Earth's atmosphere from deep space.
Right.
And they found a track in their detectors that just defied explanation.
Mm.
It curved exactly like an electron, meaning it had the exact same mass, but it curved in the wrong direction.
Because it was positively charged.
Exactly. They had found Dirac's mathematical ghost. They named it the positron. And this just blew the doors off our understanding of physics,
I can imagine.
because it meant that for essentially every fundamental particle in the universe,
Yeah.
a mirror image antiparticle exists.
Wow. So if you have a negative electron, you have a positive positron.
Yep.
And if you have a positive proton, you have a negative antiproton,
Exactly.
which means you could theoretically string those together, right? Like you could build antihydrogen.
Oh, absolutely. You could have an anti-carbon atom, anti-water, an entire anti-chemistry. You could build a perfect mirror version of the material universe.
That is wild.
And physicists have actually done the first steps of this. They have assembled antihydrogen right in the laboratory.
But, and this is a big but, you can't just leave a jar of antihydrogen sitting on a lab bench.
No, you definitely cannot.
Which brings us to the core reason science fiction writers are so obsessed with this stuff. What actually happens when this mirror world comes into contact with our ordinary world?
It is, hands down, the most dramatic family reunion in physics. When an ordinary particle meets its exact antiparticle, say, your ordinary negative electron bumps into a positive positron.
Right.
They do not bounce off each other. They do not bond to form a new molecule. They mutually annihilate.
And we use the word annihilate a lot in everyday conversation to just mean like destroy. But in particle physics, it is a very specific, absolute mechanism, isn't it?
It is. It means both particles completely vanish from physical existence. 100% of their mass is converted instantaneously into pure energy.
Pure energy.
Usually this energy takes the form of highly energetic light, specifically gamma rays.
And to understand why that is so explosive, we have to look at Einstein's most famous equation, right? E equals mc squared.
Yes. Energy equals mass times the speed of light squared. That equation is the rule book for this explosion.
Okay, break that down for us.
Well, the M is the physical stuff of the electron and positron. It is being converted entirely into E, the energy.
Right.
But the multiplier in that equation is what makes it so terrifying.
Because c is the speed of light, which is, what, roughly 186,000 miles per second?
Exactly. That is already a colossal number.
But the equation tells us to square it. So you multiply 186,000 by 186,000.
Right. And the resulting number is astronomical. Because that multiplier is so large, converting even a tiny microscopic speck of mass yields an absolutely enormous amount of energy.
Gram for gram, it's the most concentrated thing we know of.
Oh, by far. Matter-antimatter annihilation is the most concentrated, efficient release of energy known in nature. It is orders of magnitude more powerful than the nuclear reactions inside an atomic bomb, or even the core of our sun.
Okay, let me pause and deduce something here because this brings up a huge question.
Yeah.
If we know this is the ultimate, most concentrated energy source in the universe, why aren't we using it?
Ah, the power plant question.
Yeah. Why don't we have, antimatter power plants providing limitless clean energy to our cities?
It comes down to a really harsh reality of thermodynamics. You see, antimatter is not a fuel you can just mine from the Earth.
Right, you can't just dig it up.
No, you have to manufacture it. And the fundamental laws of the universe dictate that you can never get more energy out of a system than you put into it.
So the energy required to create the antimatter in the first place
Is vastly greater than the energy you get back when it annihilates.
Wow. Okay.
Yeah. You have to pour city-sized amounts of electrical power into massive particle accelerators just to generate a few fleeting atoms of antimatter.
So as an energy source, or like a battery, it's a staggering net loss.
Exactly. It will always cost you more to make than it ever provides.
That makes total sense. But it introduces an immediate, almost comical engineering nightmare.
Oh, the containment problem.
Yes, because if you are a physicist and you want to study antimatter, you have to hold it somewhere. But the moment your antimatter touches the ordinary matter of your container,
It annihilates.
right, are physicists just making it and watching it instantly destroy their equipment?
It's a great question. That was the grand challenge for facilities like CERN in Switzerland. They had to figure out how to trap the untrappable.
And their solution is a masterclass in applied physics, from what the sources show.
It really is. First, they have to actually manufacture the antiprotons and positrons. And to do that, they basically run Einstein's equation in reverse.
I love that. Running it in reverse.
It's true. If E equals mc squared tells us that mass can turn into an explosion of energy, the reverse is also theoretically true. A massive concentration of energy can condense into physical mass.
So they take ordinary protons, accelerate them to nearly the speed of light in a massive ring, and just smash them into a block of metal.
Yes. And the violence of that collision
Yeah.
creates a microscopic concentration of pure kinetic energy.
Wow.
For a sleeting fraction of a second, the conditions actually mirror the extreme energy of the early universe. And out of that pure energy, new particles just condense into existence, including matter-antimatter pairs.
But now they are flying out of the crash site. How do they catch them before they hit the walls of the machine?
They use something called a penning trap. Because these particles carry electrical charges, scientists can manipulate them using incredibly strong, carefully tuned magnetic and electric fields.
So it's like an invisible magnetic cage.
Exactly. The antimatter particles are pushed and pulled by the magnetic field so that they hover perfectly in the center of a vacuum chamber.
They just float there untouched.
Right. And the vacuum is absolutely critical. They have to pump out essentially every single stray molecule of regular air.
Because if an antiproton simply bumps into a random oxygen molecule wandering through the chamber...
The experiment ends in a flash of gamma rays.
Right. Back to annihilation.
Yep. But by perfectly balancing this magnetic cage in a deep vacuum, they've managed to hold on to complex antimatter, like antihydrogen, for minutes at a time.
Which, in the world of high-energy physics, is an absolute eternity.
It really is. It gives them the time they need to actually interrogate the mirror world. They can shine lasers on the antihydrogen to see how it absorbs light.
They can test how it reacts to outside forces.
Exactly. And one of the most fascinating tests is gravity. Physicists seriously wondered if antimatter might fall, up.
Wait, really? Fall up?
Yeah. If it was a perfect mirror, maybe its gravitational interaction was mirrored too. It's a very valid hypothesis.
That would be so weird, but what happened?
Well, the experiments at CERN recently confirmed that antihydrogen falls downward, reacting to Earth's gravity exactly the same way regular hydrogen does.
So at every turn, it seems to be a perfect symmetric reflection of our ordinary matter.
It does.
Yeah.
But physicists are utterly obsessed with finding a flaw in that reflection.
Right. They keep running these incredibly difficult experiments looking for some microscopic difference in how antimatter behaves compared to matter. Why are they so desperate to find an asymmetry?
Because if the mirror is truly perfect, then none of us should exist.
Okay, that is a huge statement.
It is, but the fact that you and I are having this conversation right now is a glaring violation of that perfect symmetry.
Take us back to the moment the universe began to explain why.
Okay, so in the first moments of the Big Bang, the universe was an unimaginably dense, incredibly hot soup of pure energy.
Right.
As the universe expanded and cooled, that pure energy began to condense into mass. Just like what happens inside the particle colliders at CERN, but on a massive cosmic scale.
And based on everything we know about physics, energy always condenses into equal pairs. If you make a particle of matter, you must make a particle of antimatter.
Which means the early universe should have contained exactly 50% ordinary matter and 50% antimatter, a perfectly balanced ledger.
But that is a catastrophic scenario. I mean, if everything is packed tightly together and every single particle of matter has a mirror twin of antimatter right next to it,
They're all going to collide.
they would mutually annihilate.
Yes. The entire young universe would have spent its first moments engaging in a blinding, complete cancellation. The matter and antimatter would have converted each other entirely back into light.
Leaving nothing.
Exactly. The universe would have continued expanding as an empty, featureless void filled with nothing but radiation. No galaxies, no carbon, no biological life.
And yet we can look out our windows. We can look through telescopes. The universe is incredibly full of ordinary matter, the stars, the planets, the dust clouds.
Right. But as far as we can measure, it is practically devoid of antimatter.
Which forces physicists to a mind-bending conclusion.
It does. In the absolute earliest fractions of a second of creation, some unknown mechanism broke the symmetry. The scales tipped.
The analogy that helps me picture this is a massive cosmic dance.
Oh, I like this one.
Yeah, imagine a dance floor with 1 billion women representing antimatter and 1,000,001 men representing ordinary matter.
Okay.
The music stops, and everyone is told to find a partner.
So 1 billion pairs form.
Exactly. 1 billion pairs find each other, and they mutually leave the dance floor in a flash of light. But there's one man left standing alone.
Because there's no partner for me.
Right. One single particle of ordinary matter out of 1 billion that had no mirror twin to annihilate with.
And that single leftover dancer is the foundation of reality as we know it. Every single star in the Milky Way, every grain of sand on Earth, and every single atom in your body is built entirely from that faint, surviving, leftover surplus.
It's just staggering to think about. We are basically a rounding error in the cosmos.
We are the microscopic residue that survived the Great Annihilation.
Yeah. But do we actually know the mechanism? Do we know what tipped the scales to create that extra particle of ordinary matter?
We don't. It is known as the baryon asymmetry problem, and it remains one of the most profound open questions in modern physics.
Wow.
Our current theoretical models simply do not produce an imbalance large enough to explain why a whole universe of matter survived.
And that perfectly explains the obsession at CERN.
Exactly. If they can find just one tiny flaw in the mirror, maybe antihydrogen decays at a slightly different rate than regular hydrogen, it might be the breadcrumb that leads us to understand why the universe favored matter.
They're hunting for the glitch in the reflection that allowed existence to happen. It is the ultimate existential detective story.
Beautifully said.
But as grand and cosmic as all of this is, we should point out that antimatter is not just locked away in Swiss laboratories or theories about the Big Bang.
No, not at all. It is deeply practical and is being used right now in local hospitals.
This part is amazing.
It is incredibly grounded when you look at medical diagnostics. There's a very good chance that you, or someone you know, has had antimatter directly injected into their bloodstream to save their life.
When I first read about this in the sources, it completely threw me. We are talking about the PET scan.
A PET scan, yeah. The P and the E stand for positron emission. Positron emission tomography.
A machine literally named after antimatter. But how does this actually work without causing, a catastrophic explosion inside the patient?
Well, it relies on the precise mechanism of annihilation we talked about earlier. When a patient goes in for a PET scan, usually to locate a tumor or see how cancer is spreading, they're given an injection of a specialized radioactive tracer.
Okay.
Crucially, this tracer is attached to a simple sugar, like glucose.
And this is where the biology meets the physics. Why attach it to glucose?
Because fast-growing, highly active cells like cancer cells consume vastly more energy than healthy tissue. They're absolutely starving for sugar.
Oh, I see. So the patient's body naturally shuttles that radioactive glucose straight to the site of the disease.
Exactly. The cancer effectively paints a target on itself by hoarding the sugar.
That is brilliant.
Now, the radioactive isotope that was attached to that sugar is unstable. As it naturally decays inside the tumor, it emits a positron.
Wow. So a particle of antimatter is born right there inside the diseased tissue.
Yes, but it can't last long because the patient's body is made entirely of ordinary matter.
Right. The environment is hostile to it.
The positron travels barely a fraction of a millimeter before it crashes into an ordinary electron inside the patient's tissue.
And they mutually annihilate.
They do. Their mass vanishes and turns into pure energy.
E equals mc squared happening inside the human body.
Exactly, but on a microscopic, entirely safe scale. Now remember the physics of that annihilation. When the electron and positron destroy each other, they release energy in the form of two gamma rays. And because of the laws of momentum, those two gamma rays shoot out of the body in exactly opposite directions. A perfect 180-degree line.
And the patient is laying inside a giant ring of detectors.
Yes. The PE scanner ring detects those two flashes of gamma radiation hitting opposite sides of the machine at the exact same time.
Oh, wow. So the computer simply draws a line between those two hits.
It triangulates the explosion.
Millions of times over.
Exactly. And by mapping exactly where these microscopic antimatter annihilations are happening, doctors can build a highly detailed, real-time, three-dimensional image of exactly where the cancer is metabolizing sugar.
That is just a beautiful piece of engineering.
It really is.
The exact same physical process matter, violently annihilating antimatter that science fiction writers use as a doomsday weapon to blow up alien spaceships.
Yeah.
Is quietly, safely, and routinely being used by oncologists to target cancer and save human lives.
It perfectly illustrates how moving from fiction to real physics doesn't make a concept less interesting. It makes it infinitely more profound.
It really does. I mean, looking at the journey we've just charted. Antimatter began as a bizarre quirk in the math on Paul Dirac's chalkboard, an impossible positive electron that basically demanded to exist.
Right.
Then we recognized it as a violently destructive force, the purest expression of Einstein's energy mass equivalence. From there, we learned how to engineer it, suspending atoms of anti-reality in invisible magnetic cages inside deep vacuums.
And finally, we harnessed that violent annihilation into a life-saving medical tool. It has transitioned from a mathematical ghost to an everyday tool.
It's incredible.
But I think the most compelling thing about antimatter isn't what we know about it, but what we still don't know.
Oh, what do you mean?
Well, we talked about the asymmetry, the idea that all the antimatter in the early universe was annihilated, leaving only our ordinary matter behind.
Right, the one leftover dancer.
But there is another highly provocative theory that physicists occasionally entertain. What if the imbalance wasn't universal? What if the universe simply sorted itself out?
Sorted itself out. You mean, what if there are pockets of antimatter that survived?
Exactly. The laws of physics allow for anti-chemistry, anti-stars, anti-planets.
Okay.
What if, far beyond the reach of our current telescopes, in the deepest reaches of the cosmos, there are entire primordial anti-galaxies, galaxies burning with anti-stars, orbited by anti-planets.
That is terrifying and amazing.
And to a telescope, the light they emit would look exactly like ordinary light. We wouldn't know the difference just by looking at them.
We would only know if an ordinary star wandered into that anti-galaxy.
Exactly. The boundary line where those two domains meet would be an absolute inferno of annihilation radiation.
Yeah.
We haven't seen evidence of those boundaries yet, so if anti-galaxies exist, they are incredibly far away.
Mhm.
But the mathematics that started with Dirac on a chalkboard still leaves the door open.
So next time you look up at the night sky, just think about that. Somewhere out there, floating in the dark, a perfect mirror image of our universe might be waiting in the distance.